Let's begin with something simple. What is a black hole, really? Forget the dramatic images for a moment. Forget the glowing rings and swirling gas. At its core, a black hole is not a thing in the ordinary sense. It is not a solid object floating in space. It is a region where gravity has become so strong that the structure of space and time themselves are bent beyond a certain limit. To understand that, we need to step back. Gravity, according to Albert Einstein, is not a force pulling objects together like a magnet. It is the curvature of space-time caused by mass and energy. If you place a heavy ball on a stretched rubber sheet, the sheet dips. A marble rolling nearby curves inward because the surface itself is curved. The marble is not being pulled in the ordinary sense. It is simply following the shape of the surface. Now imagine squeezing that heavy ball smaller and smaller without changing its mass. The dip in the rubber sheet becomes steeper. If you compress it enough, the dip becomes so steep that the slope turns into a kind of cliff. At that point, once something rolls too close, there is no path that leads back out. That critical boundary is what we call the event horizon. The event horizon is not a wall. It is not a surface you could touch. It is a boundary in space-time beyond which every possible path leads inward. Even a beam of light, which moves at the maximum speed allowed by the universe, cannot climb back out once it crosses this boundary. Here's an analogy that is closer to the physics. Imagine you are swimming in a river flowing toward a waterfall. Far upstream, the current is slow. You can swim against it. As you drift closer to the waterfall, the current speeds up. You can still fight it, but it becomes harder. Now imagine there is a line in the river where the water flows faster than you can possibly swim, even if you are the strongest swimmer imaginable. Once you cross that line, no matter how hard you try, every effort carries you closer to the edge. That line is like the event horizon. Notice something subtle. When you cross that line, nothing special happens locally. There's no flashing light, no sudden jolt. If the black hole is large enough, you wouldn't even feel dramatic tidal forces at the horizon itself. You simply drift past the point of no return. From the outside, however, something very strange occurs. To a distant observer, you appear to slow down as you approach the horizon. Your clock appears to tick more slowly. Your light becomes redder and dimmer. In fact, from far away, it looks as though you never quite crossed the boundary at all. But from your own perspective, you do cross it. And once you do, the geometry of space-time changes in a profound way. Inside the event horizon, moving toward the center is no longer a choice. It is as unavoidable as moving toward tomorrow. Just as you cannot decide to travel backward in time, you cannot decide to move away from the singularity once inside. That's what a black hole really is. Not a cosmic vacuum cleaner. Not a hole punched in space. It is a region where the shape of reality is tilted so severely that outward stops being a direction you can travel. Now let's try something more unsettling. Imagine you are a creature that lives on a flat sheet of paper. You have length and width, but no height. Your entire world is two-dimensional. You can move north, south, east, and west, but the idea of up has no meaning to you. Not because you are stupid, not because you lack imagination, but because your nervous system, your instruments, your physics, all of it is confined to two dimensions. Now suppose this sheet of paper is actually the surface of a balloon. If the balloon inflates, every point on the surface moves away from every other point. From your two-dimensional perspective, it looks like the entire universe is expanding. Galaxies drift apart. Distant regions recede faster than nearby ones. You measure this carefully. You build equations. You become confident in your cosmology. But you never perceive the third dimension into which the balloon expands. You don't even have a word for it. Now push the thought experiment further. Suppose your entire two-dimensional universe is not just sitting in a higher dimension. It is the surface of something with a boundary, a limit beyond which you cannot receive any information. Light signals emitted beyond that boundary never reach you. No experiment you perform can detect what lies past it. From your perspective, the universe is complete, self-contained. All physical processes happen within your observable region. but that completeness may be an illusion created by a horizon. In our own universe, we already live with something similar. There are regions so far away that their light will never reach us, even given infinite time, because space is expanding. This is called a cosmological horizon. It is not speculation, it follows from our best measurements of cosmic expansion. Now imagine that this horizon is not just a feature of expansion, but the edge of a black hole interior. Here is the key idea inside a black hole. There is also an event horizon. From the outside, it marks the boundary beyond which nothing can escape. But from the inside, it marks the limit beyond which no information from the external universe can enter. If we were living inside such a region, we would have no access to the outside, no telescope powerful enough, no particle accelerator energetic enough, no clever trick of mathematics could pull information across that boundary. Everything we observe would be internal. Stars would form, galaxies would collide, background radiation would fill space. The laws of physics would operate normally within the region. You could write textbooks. You could build satellites. You could argue about cosmology on the internet. And yet, the entire observable universe might be the interior of a larger gravitational structure. Notice what makes this idea powerful and disturbing. There would be no obvious sign. When you cross an event horizon, nothing dramatic announces it locally. The same might apply on a cosmic scale. The birth of our universe, what we call the Big Bang, might correspond to the formation of a black hole in some larger spacetime. From the outside, matter collapses. From the inside, spacetime begins expanding. Those two descriptions could be the same event viewed from opposite sides of a boundary. We struggle with this because we instinctively imagine ourselves looking at the universe from the outside. But we are always inside whatever reality we are trying to describe. Every observation we make is confined to the interior of our cosmic region. So the real question becomes this: are we observing the whole of existence? Or are we like flat creatures on a balloon, measuring expansion carefully, unaware that our entire cosmos is a surface or interior of something larger that we can never directly perceive? In 1915, Albert Einstein finished general relativity, a theory that replaced the old idea of gravity as a force with something far stranger gravity as geometry. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. The equations that describe this are compact and elegant, but they are also unforgiving. Once written down, they allow many possible shapes of the universe. Only a year later, in 1916, Carl Schwarzschild found an exact solution to Einstein's equations. He did this while serving on the Russian front during World War I. His solution described the space-time geometry around a perfectly spherical, non-rotating mass. What he discovered was shocking. If you compress enough mass within a certain radius, now called the Schwarzschild radius, the equations predict the formation of a boundary. Inside that boundary, the curvature of space-time becomes so extreme that all paths lead inward. That boundary is what we now call the event horizon. Here is the crucial point. This result was not invented to describe something exotic. It fell directly out of the mathematics. No speculation, no hand-waving, just the logic of the equations. Now, when physicists first saw this solution, many thought it was a mathematical curiosity. Surely nature wouldn't actually create such absurd objects. Infinite densities, regions from which light cannot escape. It seemed pathological, but nature did not consult our intuitions. Over time, evidence accumulated that black holes are real astrophysical objects. Massive stars collapse under their own gravity. Galactic centers harbor supermassive compact objects. Observations now strongly support their existence. But Schwarzschild's solution, and later, more general solutions, contain something even more intriguing. When you examine the full geometry of a black hole spacetime, especially in extended mathematical coordinates, you discover that it does not merely describe a collapsing star. It describes a connected structure with regions that resemble expanding universes. In some idealized versions of these solutions, the interior region beyond the event horizon behaves in a way that mathematically mirrors cosmological expansion. What appears from the outside as gravitational collapse can, in certain coordinate descriptions, resemble an internal region evolving forward in time. Now we must be careful. Mathematics allows many solutions that may not physically occur. Just because the equations permit something does not mean the universe chooses it. But here is what matters. The equations of general relativity do not forbid the idea that what we call our universe could be the interior of a black hole embedded in a larger spacetime. In fact, some modern theoretical models explore precisely this possibility. The idea is simple in outline, though complex in detail. Imagine a parent universe in which a massive star collapses. From the outside, it forms a black hole. From the inside, instead of ending in a singularity, quantum gravitational effects prevent infinite collapse. The interior geometry transitions into an expanding region, a new universe. To inhabitants inside that region, the beginning would look like a Big Bang. Space would expand. Matter would cool. Structures would form. They would not see the parent universe. They would only see their own expanding space-time. This is not established fact. It is not confirmed by observation. But it is not nonsense either. It sits at the intersection of general relativity and attempts at quantum gravity. The deeper lesson is this: our best equations are flexible enough to describe realities far stranger than our everyday experience suggests. And when mathematics consistently allows a possibility without contradicting known physics, it becomes something we must take seriously even if we cannot yet test it. The discomfort we feel is not because the idea is illogical. It is because the mathematics may be hinting that what we call the whole universe could be just one region in a much larger and possibly endless structure of space-time. Now let's connect this to something we actually measure, something that is not speculative at all: the expansion of the universe. In the 1920s, Edwin Hubble observed that distant galaxies are moving away from us. More precisely, their light is stretched toward the red end of the spectrum. The farther away a galaxy is, the faster it appears to recede. This relationship is now called Hubble's law. At first glance, it sounds as if galaxies are flying through space like shrapnel from an explosion. But that picture is misleading. It's not that galaxies are moving through space away from a central point. It's that space itself is expanding between galaxies. A better analogy is raisins in rising bread dough. As the dough expands, every raisin sees every other raisin moving away. No raisin is at the center. The expansion happens everywhere at once. Now here's where things become interesting. If you mathematically rewind the expansion, running the cosmic movie backward, galaxies get closer together. The universe becomes denser and hotter. Eventually, according to the simplest extrapolation of general relativity, everything converges to an extremely dense state. That limit is what we call the Big Bang. But notice something subtle. The Big Bang is not an explosion in space. It is an explosion of space. It is not matter flying outward into emptiness. It is the expansion of space-time itself. Now think about what happens inside a black hole. Once you cross the event horizon, the roles of space and time begin to interchange in a peculiar way. Outside the black hole, you can move freely in spatial directions, and time moves forward whether you like it or not. Inside the horizon, the direction toward the singularity behaves like a time direction. Just as you cannot stop moving toward tomorrow, you cannot stop moving toward the center. In the simplest classical picture, everything inevitably collapses toward a singularity. But here's the twist. From the perspective of an outside observer, matter collapses inward when a black hole forms. But from the perspective of the interior geometry, the structure of space-time can be interpreted differently depending on coordinates. In certain mathematical extensions, what appears externally as collapse can resemble, internally, a region of space-time that evolves forward in its own time coordinate. Some physicists have asked a provocative question: could the Big Bang be the other side of gravitational collapse in a larger universe? Imagine a massive star in a parent universe collapsing under gravity. From the outside, it shrinks and forms an event horizon. From the inside, instead of hitting an infinitely dense point, perhaps quantum gravitational effects cause a bounce. The collapsing matter transitions into an expanding space-time region. To observers inside that region, it would look exactly like a universe that began in a hot, dense state and has been expanding ever since. They would measure cosmic background radiation. They would observe galaxies receding. They would infer a Big Bang. They would not see the parent universe any more than we can see beyond our cosmic horizon. Now, we must be honest. There is currently no direct observational evidence that our universe is the interior of a black hole. Standard cosmology explains expansion without invoking a parent universe. The equations describing expansion, the Friedmann equations derived from general relativity, work extremely well for what we observe. But what is striking is the structural similarity. Both black hole interiors and expanding cosmologies emerge from the same underlying theory. They are not unrelated ideas stitched together artificially. They are different solutions of the same geometric framework, and that is what makes the question scientifically interesting, rather than purely imaginative. If general relativity naturally allows both gravitational collapse and cosmic expansion, then it is not absurd to wonder whether, at some deeper level, these two processes might be connected. The expansion of our universe is real. The existence of black holes is real. The mathematics describing both is the same. The question is whether that similarity is merely formal, or whether it hints that what we call the beginning of everything might be the interior continuation of something else. Now we come to the part that really tests the limits of our thinking. Even if the mathematics allows the possibility that our universe could be inside a black hole, our brains resist the idea. Not because it is logically inconsistent, but because it collides with how human intuition works. The first obstacle is that we instinctively think in terms of containers. We imagine objects sitting inside larger objects. A black hole sits inside a galaxy. A galaxy sits inside the universe. The universe, we assume, is the biggest container of all. End of story. But general relativity does not respect our preference for neat containers. Space-time is not a box. It is a dynamic geometry. It can curve back on itself. It can expand. It can contain regions that are causally disconnected from other regions. The theory does not require a simple hierarchy. When we say inside a black hole, we picture falling into a dark sphere surrounded by external space. But mathematically, the interior of a black hole is not just a cavity carved out of space. It is a region of space-time with its own structure, its own time direction, and its own causal relationships. The idea that such a region could be as vast and complex as an entire universe is not forbidden by the equations. It is simply unfamiliar to our everyday experience. The second obstacle is our dependence on visualization. Humans evolved to throw spears, climb trees, and judge distances. Our brains are optimized for slow speeds, weak gravity, and 3 spatial dimensions. When we try to picture curved spacetime or higher dimensional embeddings, we automatically convert the mathematics into mental images. And those images are almost always misleading. For example, when you see a drawing of a black hole as a funnel in a rubber sheet, that is not what it really looks like. That diagram uses an extra dimension to represent curvature. It is a teaching tool, not a literal depiction. If we mistake the illustration for reality, we trap ourselves in a false picture. The same problem appears when we imagine the universe expanding into something. We ask, what is it expanding into? But that question assumes there must be an external space. In the mathematics of general relativity, expansion does not require an outside. Distances between points increase because the metric changes. The geometry evolves. So when someone proposes that our universe might be inside a black hole in a larger space-time, our intuition rebels. We try to draw it. We want to see the outside universe surrounding ours. We want a map with labeled regions. But the concept may not fit into a single intuitive diagram. The third obstacle is more technical, but even more serious. We do not have a complete theory of quantum gravity. General relativity predicts singularities, points of infinite density and curvature. Inside a classical black hole, everything collapses to such a singularity. Similarly, if we extrapolate cosmic expansion backward, We reach an initial singularity at the Big Bang. Physicists generally interpret infinities in equations as signals that the theory has reached its limit of validity. Quantum mechanics governs extremely small scales. General relativity governs extremely massive and large scales. Where both are important, such as at singularities, we do not yet know the correct unified description. Without quantum gravity, we cannot say what truly happens at the core of a black hole. Does collapse continue to infinite density? Does it bounce? Does it tunnel into a new expanding region? The equations of general relativity alone cannot answer that reliably. So our difficulty is not merely psychological, it is scientific. We are trying to peer into a domain where our current theories are incomplete. The honest position is not dismissal and not belief. It is suspended judgment. We recognize that the idea sits at the frontier of physics. Our intuitions are poorly equipped to guide us there. Our mathematics suggest possibilities. Our experiments cannot yet decide between them. And that combination, limited intuition, incomplete theory, and vast conceptual space, is exactly where the deepest scientific questions lie. Now we arrive at the question that separates imagination from science. If we were inside a black hole, would there be any way to tell? Science is not about what sounds dramatic. It is about what can, in principle, be tested. So we have to ask, does the idea make predictions that differ from standard cosmology? Is there an observation that would clearly point to, yes, we are inside a black hole, rather than no, we are simply in a universe that began with a Big Bang? Here is the difficulty. An event horizon is not just a boundary in space. It is a causal boundary. That means it separates regions that can influence each other from regions that cannot. Information cannot cross it in one direction. That is not a technological limitation. It is built into the structure of spacetime itself. If our universe were the interior of a black hole in some larger spacetime, then the event horizon would prevent any signal from the outside parent universe from reaching us. No light, no gravitational waves, no particles, nothing. That means we could not directly observe the exterior. You might think perhaps there is some indirect signature. Maybe the large-scale geometry of our universe would look slightly different. Maybe there would be subtle patterns in the cosmic microwave background radiation, the afterglow of the early universe. Physicists have looked carefully at that radiation. It is remarkably uniform, with tiny fluctuations that seeded galaxy formation. Standard cosmology explains these fluctuations extremely well using inflationary models. So far, the data fit those models with impressive precision. If the black hole interior hypothesis predicts exactly the same observable consequences as conventional cosmology, then experimentally the two ideas are indistinguishable. And here we encounter something profound. Two very different stories about reality can produce identical observations inside a bounded region. Imagine you are inside a perfectly sealed room with no windows. The walls are impenetrable. You perform experiments with pendulums, lasers, thermometers. You construct a theory of physics that explains everything inside the room. Now someone tells you this room is inside a gigantic spacecraft drifting through space. Can you confirm or deny that statement using only experiments confined to the room? If the walls are truly perfect and no information passes through, then the answer is no. The external story might be true, it might be false. But it has no observable consequence inside the sealed environment. A universe inside a black hole could be like that sealed room. There is another subtlety. Our own universe already has horizons. Because space is expanding at an accelerating rate, there are galaxies so distant that their light will never reach us, even in infinite time. We live inside a cosmological horizon. There are regions forever beyond our observational access. So even without invoking black holes, we are already limited to a finite observable patch of a potentially much larger reality. The black hole hypothesis simply adds another layer. Perhaps our entire observable patch is itself the interior of something else. Now, this raises an uncomfortable philosophical issue. If an idea cannot be tested even in principle, does it belong to science? Physicists debate this. Some argue that if a model emerges naturally from established theory and is mathematically consistent, it deserves exploration, even if direct testing is currently impossible. Others insist that without falsifiable predictions, it remains speculative metaphysics. The honest answer is that we do not yet know whether the idea can be made testable. It depends on the details of quantum gravity, a theory we do not yet possess. So we stand in a peculiar position. The mathematics allows the possibility. Our current observations neither confirm nor refute it. And the structure of event horizons suggests that, even in principle, we might never access information about any exterior. If that is true, then the ultimate structure of reality may include layers forever hidden behind causal boundaries, not because nature is hiding them deliberately, but because causality itself forbids the question from being experimentally answered. Now we have to confront one of the deepest problems in modern physics, because it sits right at the center of this discussion: information. In everyday life, information seems abstract. It's words in a book, data on a hard drive, patterns in sound waves. But in physics, information has a very precise meaning. It refers to the complete specification of a physical system, the positions and momenta of particles, the quantum state of fields. If you know the full information about a system at one moment, the laws of physics tell you how it evolves. Quantum mechanics, in particular, treats information as sacred. The equations are reversible. If you know the present quantum state exactly, you can, in principle, reconstruct the past. Information is never destroyed. It may become scrambled or spread out, but it does not vanish. Now enter black holes. In the 1970s, Stephen Hawking made a startling discovery. By applying quantum field theory to curved spacetime, he showed that black holes are not completely black. They emit radiation. This radiation is now called Hawking radiation. The remarkable thing about Hawking radiation is that it appears thermal, random. It does not seem to carry detailed information about the matter that fell into the black hole. Over enormous timescales, a black hole can evaporate entirely through this radiation. And here is the problem. If a black hole forms from matter with a well-defined quantum state, and then evaporates in a featureless thermal radiation, where did the information go? If it is truly lost, then quantum mechanics is violated. The evolution would not be reversible. Information would disappear from the universe. But most physicists believe that quantum mechanics is fundamentally correct. So information cannot simply vanish. This tension is called the black hole information paradox. Why does this matter for the idea that we might live inside a black hole? Because it forces us to reconsider what a black hole actually is. Over the past few decades, many developments, especially from string theory and quantum gravity research, suggest that information is not destroyed, but somehow encoded at the event horizon. This idea is closely related to the holographic principle. The holographic principle proposes something extraordinary. All the information contained in a volume of space can be described by degrees of freedom on its boundary surface. In other words, a three-dimensional region might be fully represented by data stored on a two-dimensional boundary. If this principle is correct in a deep way, then the interior of a black hole is not independent of its surface. The horizon carries the bookkeeping. Now stretch this idea further. If our entire universe were the interior of a black hole, then perhaps what we perceive as three-dimensional space evolving in time could be encoded on a distant boundary surface in a larger space-time. This is not mystical language. It is a concrete proposal studied in theoretical physics. Certain versions of holography, such as the ADAS-X-CFT correspondence, demonstrate mathematically that a gravitational universe in one description can be equivalent to a non-gravitational theory defined on its boundary. We must be cautious. Our universe does not perfectly match the simplified geometries where these dualities are best understood. But the lesson is powerful. Space-time and gravity may not be fundamental. They may emerge from deeper informational structures. If that is true, then the distinction between inside and outside becomes less intuitive. What we call the interior of a black hole might be one description of a system whose fundamental degrees of freedom lie elsewhere. So the information paradox does more than create a technical puzzle. It shakes our assumptions about locality, dimensionality, and what it even means for something to be contained within something else. If information is preserved, but not in the way classical intuition suggests, then black holes are not cosmic shredders of reality. They are clues. Clues that spacetime itself may be an emergent phenomenon. And if spacetime can emerge, then the idea that our universe is the interior of a black hole is not just about extreme gravity. It becomes a question about whether what we experience as reality is a deeper layer of something whose full structure we are only beginning to glimpse. Let's slow down and separate what is solid from what is speculative. There are a few things we know with extraordinary confidence. We know that general relativity works extremely well on large scales. It predicts the bending of light by gravity, the precession of planetary orbits, gravitational time dilation, and the existence of gravitational waves. These predictions have been confirmed repeatedly. When we detect black hole mergers through gravitational wave observatories, the signals match the equations with astonishing precision. We know that black holes exist at the centers of galaxies, including our own. There are compact objects with masses millions or billions of times that of the Sun. Stars orbit them in ways that require an enormous concentration of mass in a tiny region. We have even imaged the shadow of a supermassive black hole. These are not theoretical fantasies. They are astrophysical realities. We also know that the universe is expanding. Measurements of distant supernovae, galaxy redshifts, and the cosmic microwave background radiation all support this. The expansion is not slowing down, it is accelerating. That acceleration is attributed to something we call dark energy, a placeholder name for a phenomenon we do not yet understand. We know that the early universe was hot and dense. The abundance of light elements such as hydrogen and helium matches predictions from Big Bang nucleosynthesis. The cosmic microwave background radiation has a temperature and fluctuation pattern that fits a universe evolving from a hot, dense state about 8 billion years ago. So far, nothing in this list requires that we live inside a black hole. Now let's turn to what we do not know. We do not know what happened at the very beginning, if beginning is even the correct word. When we extrapolate backward using general relativity, we encounter a singularity infinite density, infinite curvature. Most physicists interpret that as a sign that general relativity is incomplete at extremely small scales. We do not know the nature of dark energy. We do not know why the expansion is accelerating. We do not know whether the universe is spatially infinite or merely extremely large. Our observable region is finite, limited by the distance light has traveled since the Big Bang, but beyond that horizon the global structure is uncertain. We do not have a confirmed theory of quantum gravity. Several candidates exist, string theory, loop quantum gravity, and others, but none has been experimentally verified. Within these unknowns lies conceptual space. The idea that our universe could be the interior of a black hole is one possible attempt to connect cosmic expansion with gravitational collapse in a larger framework. It is not required by current observations. Standard cosmology with inflation and dark energy explains the data well without invoking a parent universe. However, the black hole interior hypothesis is not ruled out either. It is compatible with known physics at a broad level. It depends on what replaces the classical singularity when quantum gravity effects become dominant. If singularities are resolved in such a way that collapse transitions into expansion, then a new universe inside a black hole becomes a plausible outcome in certain models. The honest scientific position is therefore balanced. We know black holes are real. We know cosmic expansion is real. We know singularities signal incomplete understanding. We do not know whether these pieces connect in a deeper generative chain of universes nested within black holes. The hypothesis lies at the edge of our current theoretical reach. It is neither established fact nor idle fantasy. It is a question mark placed at the boundary where our equations still function, but our experimental access ends. That boundary between tested knowledge and mathematical possibility, is where modern cosmology currently stands. Now let's step back from equations and imagine something carefully. Suppose there exists a civilization somewhere in what we would call the interior of a black hole. They have physics. They have mathematics. They observe a universe expanding in all directions. They detect background radiation left over from a hot, dense early phase. They build particle accelerators and telescopes. They develop a theory very much like our general relativity. Inside their observable region, everything is consistent. Their equations predict the motion of stars, the formation of galaxies, the bending of light. They even discover that sufficiently massive stars collapse and form black holes within their own universe. Now imagine that, unknown to them, their entire cosmos is itself the interior of a black hole embedded in a much larger space-time. Would anything in their measurements reveal that fact? If the event horizon surrounding their universe prevents information from passing inward from the parent universe, then no direct signal would ever reach them. No light from outside, no gravitational disturbance encoding external structure, no particle carrying a message. Their entire scientific enterprise would unfold within a causally closed region. From their perspective, they are studying the whole of reality. From a hypothetical external perspective, they are studying a subregion. Here is the unsettling symmetry replace they with we. We already live within an observable horizon. Light has had a finite amount of time to travel since the early hot phase of our universe. There are regions so distant that we will never see them. The expansion of space ensures that some galaxies are permanently beyond our causal reach. So even without invoking black holes, we are confined to a limited patch. If our universe is spatially infinite, we see only a finite portion. If it is finite but curved back on itself, we still see only a region bounded by light travel time. Our data are always horizon limited. This limitation is not a flaw in our instruments. It is a structural feature of spacetime. Now consider the philosophical shift this imposes. For centuries, science progressed by removing boundaries. We learned that Earth is not the center of the solar system. The sun is not the center of the galaxy. The galaxy is not the center of the universe. Each time our world became larger, but horizons introduce a different kind of boundary. Not a boundary of imagination, but a boundary of causality. There may be aspects of reality that are not just currently unknown, but fundamentally inaccessible. If we are inside a black hole, then the parent universe is not merely distant. It is causally disconnected. No experiment, no matter how advanced, could probe beyond the event horizon that defines our cosmic region. That does not mean the idea is meaningless. It means its truth or falsity may not alter any observable prediction within our domain. And here science meets a subtle limit. Physics builds models that explain observations and make predictions. If two models produce identical predictions for all possible observations within our horizon, then experimentally they are indistinguishable. Choosing between them becomes a matter of theoretical elegance, consistency with deeper principles, or future unification, not direct measurement. This is not a failure of science. It is a recognition of its scope. Science operates within the domain of observable consequences. If reality contains layers permanently hidden behind causal barriers, then our theories will always describe the interior view. The profound shift is this: what we call the universe may mean the region accessible to us, not necessarily the totality of existence. And that realization changes how we interpret cosmology. We are not outside observers mapping reality from above. We are participants embedded within a bounded region, constructing models from the inside, always peering outward toward horizons we can approach but never cross.